Galaxies housing all stars are fundamental constituents of the universe, meaning stars do not form outside or in between galaxies. Galaxies are classified by morphology, meaning their shape and size. We do have three types of galaxies: spiral, elliptical, and irregular. First, starting with elliptical, these galaxies are spheroidal and have a smooth overall structure, purely bulge with no disk, unlike the spiral galaxies we'll come to talk about. There's little to no star formation due to the gas supply having already been largely consumed early towards the formation of the galaxy. As we can see, there is a equation of sorts to name these galaxies using their major and minor axes. 10 times A minus B over A. So as we can see with this E6 galaxy, we use the minor and major axes to get that 6. Now onto spiral galaxies. These galaxies are classified by the relative bulge to disk ratio. We can see between types SA and SC, it is in order of decreasing bulge to disk ratio. There are also barred spiral galaxies, where the spiral arms are attached to opposing sides of a bar of stars, ranging from SBA to SBC. The dust and gas mass fraction is typically 10 to 50% of the entire disk. And so it's safe to then say there's constant star formation over the life of the galaxy, and formation occurring mainly in the spiral arms. We will then talk about how density waves in spiral galaxies impact their structure. Density waves are material waves that cause the density of a medium through which it passes to fluctuate around its mean value. For spiral galaxies, the angular rotation rate is slower for the outer edges than the inner region. However, this then raises a problem, because we then expect the spiral arms to be tightly wound by now, and not be visible at all. We then look to density waves to help solve this problem. Imagine the density wave in the spiral pattern as the spiral galaxy rotating at a certain speed. The gas orbiting the galactic center then meet the density wave, slowing down as it passes through. The local density increases and star formation occurs, creating the spiral arm. And finally, we have irregular galaxies. These galaxies have no general shape or size that we can attribute to them. However, there is a lot of star formation due to a considerable amount of gas and dust present in these regions of space. Here we have the small and large Magellanic Clouds. Like many irregular galaxies, are satellites to bigger neighboring galaxies, and in this case, they are satellites to our Milky Way galaxy, which is a barred spiral galaxy.
Orbital velocity. From previous studies at A-level and classical mechanics, you should know the following two equations. F equals g m1 m2 over r squared, and F equals mv squared over r, which are Newton's law of gravity and centripetal force respectively. From these two, you can derive an equation for orbital velocity by equating them both. We equate the two as, for example, a satellite orbiting the Earth will have the force of gravity pulling it towards Earth. So it must have an equal and opposite force to stop it from spiraling into Earth by gravity. The derivation is as follows. We equate centripetal force to gravitational force, so mv squared over r equals g big M small m over r squared. From this, we can cancel out an r in the denominator and small m in the numerator. Rearranging, we get v equals root g big M over r, where v is the orbital velocity of an object in the system. Something to note is that the velocity of the object does not depend on the mass of the object itself, and only the mass of the larger object it's orbiting. A real application of this is looking at orbital velocities of stars or dust in galaxies. Astronomers use real measured data and compare it to the predictions made using the equation just derived. Looking at the graph, the dotted line A is the velocities calculated of stars as you move further away from the galactic center. As our equation shows, orbital velocity varies inversely proportional to root r. This results in the curve decaying as we see. The line B is the actual measured orbital velocities of the stars, which is widely different to our prediction. This leads to the theory of dark matter. Looking back at our equation, we can see that this must be due to mass. The right-hand side includes g, m, and r. G is the gravitational constant, so we can assume this isn't the reason for the discrepancy. We can also assume that the measured distance from the center is correct, which leaves only mass to be the anomaly. We can see from the graph that the galaxy's outer region's stars have much greater velocities. This cannot be explained by our theory, unless there is more mass present than what we can see. This is dark matter.